Better not press the leave meeting when it says, "Are you happy that you're being recorded?" Thank you, Adil. Thank you for the invitation, and thank you for organising the whole series. I've very much enjoyed the talks that I've been able to attend. It's been great. So today, I thought I would take a rather broad view of the sort of packing problem I'm going to tell you about, rather than a deep dive into any one of them. Almost all of them are unsolved problems, and so what I'm going to present is conjectures, but of course, if you have ideas, then there's lots of things to discuss and lots of things for people to work on. Optimal packing of a finite collection of deformable objects, and the subtext here is I'm thinking about foam structure, and so one of the things I'll do is explain the relationship between the title and foams. And so another way of thinking about this is minimal surface problems. And so the question that underpins everything I'm going to say today is, how does one partition space into cells with least surface area? And for the moment, let's talk about equal volumes. So of all the ways that you could divide space, which of them has the least surface area? That is known as the Kelvin problem, and the solution to that problem is not known. And of course, there are many candidate solutions, which maybe each win in their own particular way, but just a completely general solution is not known. But what is the case is that every time you make a foam in your bath, in your washing up bowl, and you wait until it reaches equilibrium and you wait until all the liquid has drained out from between the bubbles, you have a realization of a space filling pattern. And it's very unlikely that you will find the global minimum, that is the solution of the Kelvin problem, but you do have a realization of a local minimum. And so what I'm going to talk about is, I think, somewhat esoteric in terms of what one is trying to do, find the global optimization, the solution to the global optimization. But if foams could rearrange to seek out the lowest of many local minima, this is what they'd be doing. And so they'll be finding the global energy minimum for a foam of equal volume bubbles. And really, so the picture in my mind is always this sort of foamy structure, where the struts between the bubbles are very thin, there's very little liquid in there. So having said that the Kelvin problem is not solved, Kelvin's own solution is very good. Kelvin suggested a structure with a single bubble that is repeated. It's a polyhedron. Well, it has 14 faces, and in fact, once you relax it to minimize its surface area, the hexagonal faces become slightly curved, which I think you can see in the picture. So he called it a delicate curvature. And I have to be careful what I say because Rob is here and Rob will correct me. But I think it's probably accepted to be the monohedral tiling with least surface area. That is the tiling in which all the bubbles are the same, with the same orientation. But it's not, it turns out, the best. So 100 years after Kelvin, Dennis Weir and Robert Phelan came up with a different structure which has lower surface area. So it consists of 2 pentagonal dodecahedra and 6 14-faced polyhedron sort of barrels. You can see the hexagonal face front and foremost there. It's inspired by what's known as a Frank Caspar phase, in metallic alloys, which is known as A15, which was, I think, the number of the bus that Rob Phelan used to get to Trinity, which is maybe explains why they chose this one to look at first. The surface area is lower than the Kelvin structure by 0.3%. And so here's the game, in that we're looking at tiny differences. All these foam structures with bubbles of equal volume are very similar in their energy, in their surface area. The Weir-Phelan structure, as it's known, has its own piece of fame. It was what was made into the swimming pool for the Beijing Olympics. And it doesn't look like a foam of equal volume bubbles, but that's just because of the way that it's been sliced. The numbers I'm giving you, the surface areas, are all going to be taken from, as Adil mentioned earlier, Kembrachi's surface evolver. So I would disagree with what Adil says. I'm not the expert on surface evolver. Kembrachi is the expert, and I am merely a keen acolyte. But if you haven't come across surface evolver and you want to do anything with minimization of energies, it is a remarkable piece of software. It is still free. And what you see on the screen now, is work by Andy Kranick, where he has tested many ordered and disordered foam structures to look at their, it's labeled energy, that's just surface area for us, versus the average number of faces of the bubbles. So you see Kelvin over at the bottom right, and you see Weir-Phelan, of course, the lowest point. The energy is the surface area per bubble for bubbles of unit area. And so you can see it's a little bit less than the surface area of a cube of unit volume, which would be 6. So much better than packing with cubes. There's a whole range of disordered structures made with various methods. They never quite get down to Weir-Phelan, but there is also this row of tetrahedrally close packed structures, which also do very well, and Weir-Phelan just seems to win. But there is no proof that you won't find anything better. If you were to propose a bubble that would be the same and would fill space, based on Euler's theorem, it would have 13.4 faces, and each face would have 5.2 edges. Clearly, this is not realizable, but it shows you why perhaps Weir-Phelan is better than Kelvin, is that it has many more 5-sided faces, and so that brings the average F down towards that 13.4. But clearly that's not a proof. To my mind, there's no reason why the best solution to the Kelvin problem should be periodic. And given that having a lot of 5-sided faces seems to be advantageous in reducing the surface area, I was privileged to work with Remy Mosseri, Jean-François Sadoc, and François Grenaire, whose name is going to reappear several times during this talk, to try some candidate quasi-crystal structures. The problem, of course, is that you can't use periodic boundary conditions because these structures don't, by definition, don't repeat. And so we made clusters of quasi-crystals, made them slowly larger and larger and larger, and looked at what happened to the surface area. So we truncated them to be circular clusters and put layers of quasi-crystals in. And the result is still, unfortunately, the Weir-Phelan is best. But some of these quasi-crystals, the red pluses, really get very close to Weir-Phelan. And so I haven't completely given up. This cluster down here, as you make the cluster bigger, the surface area jumps around, and the result is a very tiny bit above we're feeling. So perhaps there are other quasi-crystalline structures that one should try. Perhaps make the clusters larger. Maybe we could get below we're feeling. So to make a fairer comparison, we also tried clusters of we're feeling bubbles, which is why you see lots of little coloured in triangles just above the main we're feeling triangle.
Can I just say, I think I know it, I'm reading your caption, but can you just describe a little bit FRMS? So is 0 the famous 13.397?
Exactly right, exactly right. Yep. So we needed some axis to compare these things on, and rather than number of faces, we chose the difference from the ideal bubble, the ideal but unphysical bubble, and then everything except Kelvin lies on a line.
I see. But you go both. I mean, I saw in the earlier phase portrait that there were some that had lower than that number for some curious reason. So you're taking the square. So are there some things that happen to be far to the right, but that have since you're squaring, that have actually a smaller average number of faces? I'm just wondering there's a lot of examples on here. So do they all have...
and I haven't put in all the disordered structures from Kreinig, and so I don't know where they lie, whether they lie further to the right.
But I was curious about 12 in these clusters. You might see a lot of 12s now because you're not enforcing. Oh, maybe not.
Yeah, I don't remember, Rob.
Thanks.
Okay. And so one can try things on these 3D packing problems, and it's very difficult to make progress. And so my idea to make progress was to retreat to 2 dimensions. And there we do have an ideal bubble that works very well, that tells you the least perimeter division of the plane into cells of equal area. And that, of course, is the hexagonal honeycomb. And Hales proved that 15, 20 years ago, I think to everybody's satisfaction. And again, there is a foam analogy. One can make a 2D foam by squeezing a 3D foam between 2 parallel plates, normally glass or perspex plates, so that you can still see in. And then as a consequence of the foam minimizing its perimeter, every film is a circular arc. Those arcs meet in 3s at 120 degrees. And if there are solid boundaries, which I'll introduce later, they meet those boundaries at 90 degrees. So it's a system where you can very easily see what's going on, and it's somewhat less computationally expensive to try many different possibilities. So what do we know? Let's even retreat from filling the plane. You could start thinking about bubbles with different sizes and how they fill space, but instead I want to go to finite collections of bubbles and say, if I take 1, 2, 3, 4, and so on bubbles, how should I arrange those bubbles so that they minimize the total perimeter? By total, I mean internal and external perimeter. And so for n equals 1, 2, and 3, there are proofs. One is the classic isoperimetric problem, circle in 2D, a sphere in 3D, and so on. And that's I think that's known for many dimensions. 2 bubbles, that's the double bubble problem, again known in many dimensions. 3 bubble problem, Wishiramala proved that in 2D, and I think there's some more recent work where they take that into higher dimensions. But as n increases, it's remarkably difficult to say what is best. And so our approach was to try and do something numerical and work out what the answer was, even if we couldn't show that it was the answer. And so you see candidate solutions from a numerical search for different numbers of bubbles, and they're coloured in a way that I'll describe in a moment, more or less according to their number of sides. So one way to approach a proof might be to enumerate all possible topologies, and the number of possible topologies gets very large very quickly, but we can do something. One could do a numerical search, try and explore some sort of energy landscape. And the first assumption I'm going to make is that each cell in each conjectured minimal perimeter solution is connected. I haven't broken it up into small pieces and distributed them around all the other cells. So in looking at these clusters, sort of questions one might ask in trying to predict what would be good candidates to try. Questions like, can we expect the periphery to have any particular shape? Right, is a cluster that has a circular boundary likely to be better than something that, for example, has a hexagonal boundary? Or is it more important just to minimize the number of defects, to have as many hexagons in the bulk as possible and as many pentagons on the periphery? And once you accept that you're allowed some defects, where should you put them? Should you put them in the middle? Should you put them as close to the boundary as you can? Let me try and answer some of those questions. And so we're going to do some numerical shuffling first, and that's through what we call topological changes, T1s. Take any internal edge and flip its orientation and reconnect it to its neighbors. And I don't have any sort of ergodic theorem, but one explores a large proportion, I think, of the energy landscape. And so here's, this one's constrained in a circle, but similar idea. Here's the sort of process that we go through with Surface Evolver. We try many things, sequences of these T1 shuffles, and at the end of the calculation, we just save the one that had the least total perimeter. So the colouring is according to the number of sides, sometimes called topological charge. So in the bulk, you would like hexagons, and so if the number of sides n is different to 6, you would choose to colour things differently. And on the periphery, you would expect hexagons. That's what you get if you cut something out of a hexagonal lattice. But there's always going to be a total charge of 6, not 0. It means, for example, that you have 6 four-sided bubbles around the periphery. And so here are some candidate solutions up to 15. And it's rather difficult to say, I think, whether you see a pattern. Never see more than one yellow bubble, that is a 7-sided bubble in the bulk or a 6-sided bubble on the periphery. Mostly, but not always, positive defects are confined to the periphery. But then you see that 19 is a particularly special case. 19 is a hexagonal or a central hexagonal number, magic number. And there, everything works out very nicely. So any theory might be predicated on how far you are from the nearest hexagonal number. The next hexagonal number is 37. And so that also works very well. And again, between hexagonal numbers, there's often just one defect pair. And you can see for 34, it sits in the middle.
Can I interrupt with a little comment? So if you go back to one slide, look at 27.
Yeah, it's
So it's sort of a sub-hexagonal number, I guess, but it has a nice symmetry also.
sorry, my light's just gone off because I've been sitting still for too long. It's as if it's been cut from a hexagonal lattice, but it doesn't have the symmetry that you would expect for a hexagonal number.
That's right, but it has the other symmetry you might expect, which is it's. I mean, there's several that have, you know, for example, 27 and 30 have some nice. You know,
Yeah.
This is a comment I was going to make, is that every flat torus has this 180-degree symmetry, and special ones have threefold, sixfold, and fourfold. But I guess keeping track of those might be fun in your process. And I'm going to stop.
Right.
Now.
Right. Yeah. And we stopped at, of course, 42. And then came back to the problem again with François Garnier, and asked what happens as these clusters get bigger. Can we pin down this question about what happens around the boundary of one of these optimal clusters? So what you see is two different clusters with the same number of bubbles, 200. One is a circular region cut from a hexagonal lattice, so the periphery should be as short as possible. The other is a portion of a hexagonal lattice without that circular symmetry, so the periphery is certainly longer, but in fact it does have lower perimeter. And so the question is, as you go to larger and larger n, how important is the length of the periphery in determining what sort of shape of cluster you should start with? So hexagonal numbers of the form 3i squared plus 3i plus 1, comparing the periphery 36.718 with a circular cluster with a lower periphery but a higher perimeter. So the question was, is there a value of n above which the preference for perfect hexagonal arrangement fails because the periphery is so much longer? And I discussed this with Frank Morgan, who many of you will know, and he was adamant that for very large n, it must be circular. And if he's right, then that very large n is very large. So let me explain. We tried to compare different ways of making these large clusters, and we went all the way up to over 100,000 bubbles, and a circular cluster is never better than something with the symmetry that Rob likes. And so what we tried to do is, we called them hybrid clusters, somewhere in between hexagonal and circular, and just cut the corners off something taken from a hexagonal pattern. And indeed, this is better than hexagonal and better than circular when you have more than about 38 shells of hexagons. That is 4,500 bubbles. And so in a vain attempt to improve my Erdish number, I published this with Frank Morgan and went up by 1. In fact, we went up to 170,000, and then circular clusters are still not best. These sort of hybrid clusters where you take something hexagonal and cut the corners off still do best. And so, again, a conjecture that's still unresolved. What happens in the limit of very, very large clusters? But if anybody has
I have a question again. So when you cut the corners off, are you cutting them? Yeah, you're drawing a good picture. Are you cutting them almost linearly, or are they little circular cuts? I mean, it seems like they're very small cuts to reduce it. The corners is like a first variation that lets you cut them off a little bit, but then it stops being.
Yeah, it's somewhat ambiguous. So we tried 6 different ways of cutting bits of corners off, or removing a side, or just taking things from one corner. And I can't remember exactly which one this is. I'd have to go back to the paper, Rob. So.
Quick question also from my side. So is there a can you say a bit more why it should be circular? Because if you think of it from the perspective of a crystallographer, then faceting is very, very obvious. I mean, there are things like wolf shape and other where lowest energy or lowest free energy states are faceted. So why would you think that bubbles is different and wouldn't form faceted crystals?
Just because in contrast to crystals, I mean, you're just counting up the sum of all the lengths of the periphery of the edges, and so.
But you're also doing that in crystals in a way. The surface, the energy of the surface is sort of the integration of over a surface, so it's not so different.
Right,
but that's anisotropic is the point. Whereas this is at the boundary. If you have pure perimeter, it should prefer isotropy on the one hand. That would argue for a circle. Whereas in the bulk, you see the hexagonal lattice, which might bias to introduce like a wolf shape or an anisotropic effect. And the question is which one wins.
Okay.
I think Ian just nailed it. Yeah.
Thank you.
Thanks.
Okay. So what if we constrain these things and say we choose the boundary, and where do the bubbles go, where do the cells go, so as to minimize the arrangement inside? And so the question is, how does the shape of the boundary change the topology of the minimizer? And the way I prefer to tell it to 14-year-olds, and so I'll treat you like 14-year-olds, is given that your mother's told you you're not allowed to lick the knife after cutting up a piece of cake, how should you cut that cake so as to use the least amount of cutting, so you get the least cake left on the knife? And of course, that requires that you're going to share it, which may not be a given. And so let's go all the way to n equals 2. And of course, you cut the cake in half, and that's the least amount of cutting, and you get exactly the same area. For 3, it's the same solution we saw from the Wishy-Ramala proof. And then, of course, it starts to get interesting because this 120-degree condition starts to manifest itself. If you're minimizing the perimeter, the internal perimeter, as well as the peripheral perimeter, your edges should be meeting 120 degrees. And then, of course, for n equals 5, it becomes almost uncuttable.
I tried that with a brie at a very fancy event, and I was pretty much thrown out of the event.
Same question for a triangle. I set this as a student project, which was a chance to show my ignorance. Of all these 3 ways of cutting up a triangle into 4 pieces with the same area, which of them has the least perimeter? And so the student went away and calculated these, and the one on the left has the least area. And then he said, but I went through all the possibilities, and of course, that symmetry is not important. That you choose the solution that I just showed you for a circle. And so 1-0 student to supervisor. And so we can do this for many sort of boundary shapes, and it perhaps would be interesting to ask, as you change the boundary, does the candidate that you find inside stay the same? And in fact, it very rarely does. So for a hexagonal boundary, you see, of course, the hexagonal number, sorry, circular boundary, the hexagonal number on the right, n equals 37, has the same candidate. But apart from that, it just doesn't work. Here's the hexagonal boundary. Again, 37 is good. 34 is more or less the same in all three. And it's tempting to suggest that for that hexagonal case, you can predict what's happening. There's that defect pair, the 5-7 pair seems to just move through the interior, although unfortunately it doesn't extend all the way up to 42. Pentagonal boundary, an extra defect for 35. Square boundary, many defects, really hard to see anything nice coming out of that. And then the triangular boundary is beautiful. With an equilateral triangle, there is exactly one defect pair, or sorry, at most one defect pair, and it jumps through the lines of hexagons from one boundary to the other and back again as you go between triangular numbers. And so 36 is a triangular number, no defects at all. And that pattern does extend all the way through all candidates that we looked at. And so that's really quite elegant. Just to show you some data. So if you take the data for free clusters and fit that to a functional form, then you would like 3n for all the hexagons in the bulk, where each interface is shared between two hexagons, plus a term proportional to the length of the periphery, which should go as the square root of the number of bubbles. And so we found k is about 0.45, subtracted that from all the data. And so starting at the bottom, you see a small variation about that fit for the free clusters, and of course the dips are at the magic hexagonal numbers, and the sort of so I'm not sure if that was a question. And then move up to the circle, hexagon, pentagon, and you still see those dips at the magic numbers, but also some extra dips in between them, until you get up to the triangle, clearly highly constrained, and so rather high energy, but a beautiful repetition of the arc, and sort of nothing out of place. So to try and move briefly out of the plane, here's an experiment. Adil and I were talking about Canberra earlier. This was Tim Senden and Jean-Marc D'Amelio did an experiment in Canberra where they enclosed a foam between two concentric spheres, or at least hemispheres. And so that inspired us to try confining two-dimensional foam to the surface of a sphere and asking what the arrangement of bubbles is in the least perimeter candidate. And can we predict the minimum length? Again, there are some proofs for some particularly nice numbers: 3 bubbles on the sphere, 4 bubbles on the sphere, and 12 bubbles on the sphere. But we just searched numerically for all the other n to come up with candidates. And so the first thing you see there is 11 bubbles, and that's the first time that a hexagon appears. But as you can see, there's still a quadrilateral face there. For n equals 13, we found the topology of the Matsky cell. Matsky did an experiment on a foam packing, and this was the most common bubble shape that he found in a 3D foam. And beyond n equals 13, we don't see any more quadrilaterals. which means that for 14 and above, everything consists of pentagons and hexagons. And in fact, it's a packing that has exactly 12 pentagons, as you, I'm sure, know from footballs, and the rest must be hexagons. And so these are known as fullerenes. And so it seems that the minimal perimeter candidates on the sphere for n greater than 14 are fullerenes. And of course, the most wonderful example is the carbon-60, and the link between the number of carbon atoms and the number of faces is shown there, C equals 2 times n minus 2. And so the conjecture is that minimal perimeter tilings of the sphere are all fullerenes. And so I was introduced to this numerical tool CAGE from carbon chemistry, which allows you to enumerate all possible fullerenes. And I didn't know that there was more than one fullerene for each n, and to see which of them has the least perimeter. So I mean, the boring bit is that we compared each candidate with its equivalent in the atlas of fullerenes, and in most cases put a number to it. But more remarkable is just to look at the perimeter, or at least the perimeter compared to the perimeter of the same number of hexagons, and you see that remarkable drop at n equals 32, which says that not only is C60 very important for chemistry, but n equals 32, its foam equivalent, seems to have remarkably special properties. So it's probably the most symmetric cluster of bubbles on a sphere. And so it seems that enumeration is something worth pursuing, because there is this one-to-one correspondence.
Sorry, can I ask a question? It's Axel from Dresden.
Sure.
So if I remember right, for your fullerenes, or for like that's related to like equal distribution of points on sphere, and so in these fullerene structures, the cell size is not identical, I think, right? So the pentagons are a bit smaller than the hexagons.
Yeah.
But this is not important for your comparison, and you get the same structures. Is this what you're saying? So
we do get the same structures, but with the restriction that all areas are equal. We don't always get the if you like, the nicest fullerene for a given n. So they have all these rules about how far there is between pentagons, and they don't all apply to the foam problem. Isolated pentagon rule.
Okay.
And
okay.
so, yeah, okay. So there is a correspondence between, and back in the plane now, 3 connected simple cubic graphs and 2-dimensional clusters of perimeter minimizing cells or bubbles. And so the most recent thing we did was to do an enumeration of bidisperse clusters to try and find the least perimeter version. So very unsubtly, that was published in EPJE a couple of years ago. And we could only go as far as n equals 10 bubbles. After that, the number of candidates that you enumerate and then have to import into Surface Evolver to find their minimum perimeter, and then change the ratio of areas between the large and the small bubbles, just became unmanageable. That's not to say it won't become manageable in the future, but for us, it was too much. And so one of the questions we can at least give evidence for, even if we can't answer it, is in the optimal cluster, where do you find the small bubbles relative to the large ones? Do they all like to group together in one region, or do they spread themselves out around all the other bubbles? And so here, for example, is all partitions of the disk into 5 regions. And clearly, with an odd number of bubbles, you can't have the same number of large and small, so we had an extra large in this case. We also then tried the extra small. The area ratio in that picture is 2, and so it's possible with n equals 2 to have all of the enumerations without having to force topological changes, although you can see that there are candidates where some of the edges are very short, very unlikely that they would be optimal. We define the polydispersity because we expect that to affect the total perimeter quite strongly, and then scale all our data by 1 plus the polydispersity, so that the graphs, the lines are more easy to compare. So we implemented each of the clusters in Surface Evolver with a range of different area ratios, and then slowly varied the area ratios to interpolate between them. So when you see a sudden drop in the graph, that's a topological change, and something that we started with was no longer stable for the higher area ratio. But it's clear in this case that that candidate with 2 small bubbles separated and opposite sides of the circle is optimal whatever the area ratio. But as you increase the number of cells, it starts to become much more interesting. So this is the largest number we chose. You can see there are many candidates, and we explored each of their trajectory as the area ratio varied, and then picked out the region over which each of them had the optimal pattern for that area ratio. And so we've got 5 different possibilities for area ratio from 1 to, well, above 6. It seems not to change. And so the conclusion is that small bubbles cluster when the area ratio is small. When the area ratio is large, those small bubbles like to sit in the gaps between the large bubbles. So I am out of time. I shall conclude rather briefly. I've showed you 4 or 5 different minimal perimeter problems, minimal surface area problems for packing bubbles. And we have some conjectures, we have some evidence, but we don't have any definite results for quasi-crystalline space fillers, trying to beat the Kelvin problem. We've looked at finite planar clusters, or those confined within shapes, and my favorite one is the equilateral triangle, where it seems that there's a pattern that perhaps one could do something with. We've seen fullerenes on the surface of a sphere, and we're starting to explore bidisperse clusters. So, of course, one question is, does this help someone to prove something? Another question is why? Why do we see those particular patterns? Another why is why do we do this? It's interesting. It's perhaps informative for looking at foam structures. Perhaps it's informative for how you pack things inside circles or in hexagons. Because in my mind, there's something of a correspondence between minimizing the perimeter of these things and minimizing the deformation of each individual cell, so that it's fairly isotropic. I also wonder whether it applies to cellular structures in biology, which of course are tightly packed, and whether one could improve their functionality by changing the packing. And finally, I suspect many of you have your own favorite algorithms and software for doing things. And I wonder whether, as we've in the way we've combined cage with surface evolver, whether there are other pairings where nice candidates could be found, and then one moves to surface evolver to try and really get a highly accurate estimation of their surface area. That's all I wanted to say. So thank you very much for listening.